In this final video for Unit 2 velocity, we're going to introduce one final concept that's integral to the unit velocity, the unit on velocity, and that's something called a motion map or a motion diagram. An example that I chose involves a chicken. I don't know why, just a chicken. And I went ahead and put a scenario in which case the chicken was moving. I want you to imagine a chicken. This is one chicken, but what I've done is I've set up a camera to take a snapshot at every second. So the time interval is even. So every second the camera takes a shot, and I've compiled the pictures as so. You'll notice that the chicken is moving at a constant velocity up here. Now, how do I know that? I know that because the space in between each chicken spot is exactly the same. Remember, the camera was snapped every second. So if the distance between each subsequent shot is the same, we must conclude then that the chicken was moving at a constant velocity for those first 5 seconds. One thing I will do, and we'll see later, is we will represent the object with a dot. So if you can imagine dots, and my dots aren't very good, but you get the idea. If we draw dots to be our particle, you can see the distance between them is the same, and therefore the velocity is the same. Then what happened is the chicken changed positions. Somewhere between this second and this second, the chicken turned around. Notice that the chicken did not actually move back, but simply just stopped. So when you see dots on top of each other like this is indicating that the object is at rest. Finally, we see the chicken is beginning to move, and we see that every second the distance between the two dots is actually greater than what it was up here, indicating or concluding that the chicken must be moving faster down here than it was up here. This is called, like I said, a motion map or a motion diagram. Now, it's not enough just to put dots, but we also need to show vectors, and specifically velocity vectors. What that means is we're going to draw arrows. Now, arrows are very useful and beneficial in physics because they give a couple pieces of information that's very important. First of all, the length of arrows. If I had an arrow that looked like that versus an arrow that looks like this, the longer arrow represents an object is moving at a faster pace, simply because it's longer. So the length of the arrow indicates the speed. The second thing that's informational about arrows and velocity vectors shown as arrows is the direction. At the top, the chicken was moving to the right. The bottom, the chicken is moving to the left. So the velocity vectors or velocity arrows not only show magnitude by their length, but they also show direction by which way they're pointing. That's why velocity are vectors, because they can be drawn as vectors. So what we need to do is on top of the dots, we need to actually show the vectors or the velocity arrows. So, and I'm going to go ahead and try to do that like this. That way I can go ahead and make sure they're nice arrows, and I'll make that the right color. So I'm going to go ahead and draw an arrow like that right on top of the dot. Same thing here, and I need to make sure that the arrows are the same length because I'm wanting to show that the velocity is constant. If the arrows are the same length, then that means that the velocity is constant. Now, I'm not going to draw an arrow on this spot or on this spot because the chicken, or the object being the chicken, was at rest. The chicken doesn't start moving until time right here. And notice I'm going to make the arrows longer here and here, and I'm going to go off the page a little bit, but you get the idea. Finally, we want to make sure we have some way of showing that the arrows are in fact equal. After all, I only guesstimated at this, but they may in fact actually in real life not be the exact same length because I didn't take out a ruler. So there's an easy way to show that the arrows are the same length, and that is by drawing a little slash mark in between the on top of the vector arrows. The slash marks indicate that all 5 of these arrows are the same length. For these arrows down here, I'm going to go ahead and draw 2 slash marks for each one, indicating not only are these two the same length, but they are bigger than the ones up here. And that is a motion map. It is a pictorial representation of what is going on with an object. So let's go ahead and look at an example. It says, given the following graph, explain the motion, draw the velocity versus time graph, motion map, and then any other information you can think of. Okay, so let's go ahead and examine this first, and then we'll focus on the details. We're looking at a position versus time graph, and it doesn't tell you, but we can assume the position is measured in meters and the time is in seconds. Okay, for the first 2 seconds, the object is not moving because the slope is 0, and since the slope is 0 on a position versus time graph, that means the slope is 0 meters per second. Same thing for down here as well. Now, for this right here, the slope goes down 3, so -3 in 1 second. So it's -3 meters per second. And then the object right here goes up 1 meter in 2 seconds. So that means positive 0.5 meters per second is the velocity there. Now I don't have the axes here, so we're not going to actually draw the velocity versus time graph. We've gotten lots of practice with that in video 2. But I do want to show the motion map. Now, there's a couple important key things that we need to make sure we draw in a motion map. We need to make sure, first of all, that we establish an origin. And we establish an origin by simply drawing a line, a vertical line just like this. Then we need to establish a positive direction. It is common practice, although not required, to make the positive direction to the right. By drawing an arrow connected to your origin pointing to the right, it is indicating that this direction is the positive direction. So this is going to be our reference for our motion map. Now, let's go ahead and draw in our motion map dots. Since the motion happened in 7 seconds, I'm going to make sure that there are 7 dots. Alright, now notice the object did not start at the origin, but actually started ahead at the 5 meter mark. So I'm going to draw my first dot right about here to indicate that I'm starting away from the origin. This would be where time equals 0. And I want to make sure I actually write that below so I don't get confused. Time equals 0. So I know that this is the beginning dot. So this represents right here. Then at time 1 second, the object is still motionless. Now rather than drawing the second dot right over it where you can't even see it, we like to draw the dots on top of each other if they're still at the same position. Now, at this time equals 2 seconds, we can assume that the object is beginning to move. So I'm going to go ahead and draw that third dot representing time equals 2 seconds. Now, right here, and I'm going to draw a velocity vector pointing to the right. Excuse me. Let me erase that. So here is at time equals 1 second, so right here. And then time equals 2 seconds, I'm going to put right here. Okay, when I draw my arrow, I need to make sure it's pointing the right way. Remember, this velocity was negative, and since I said positive was to the right, that means negative must be to the left. So I'm going to draw my arrow, not very straight, I do apologize, but I'm going to draw my arrow pointing to the left to indicate the velocity is negative. Then, at time equals 3 seconds, the object has stopped again. So I'm going to draw a dot here, but with no arrow coming out of it. Now I want you to notice something. Has my dot made it back to the origin yet? No, because right here, it's at the 2 meter mark. It hasn't made it back to the origin just yet. So I want to make sure I'm drawing things to scale as best as possible. At time equals 4 seconds, the object is still at rest, so I'm going to draw it right on top. Then at time equals 5 seconds, we can assume the object is now on the move again. The velocity here is positive, so I'm going to draw a dot here, but I'm going to now draw the arrow this way, And notice my arrow is shorter here than here. Maybe I'll even put 2 slashes there and 1 slash there to indicate that they're not the same length. And then finally, I'm going to draw a dot going this way and a dot going this way to finish it off right here. And I'm going to put slashes there so I know that the velocity is the same. Now, there's one thing in here that I need to make sure I change, and that is making sure, notice that according to my motion map, I'm saying the object ended right here, somewhere past where the object actually started. When in reality, the object never makes it back where it started. It started at the 5-meter mark, but only made it back to the 3-meter mark. So maybe what I can do, and this is why you always want to have pencils on physics tests so you can erase, is I'm going to actually pull this starting point back here. And I'm going to get rid of this stuff right here. Excuse me. I'll just erase that. There we go. And my t equals 0. I'll move over here. And I'll move this dot right here. This is the joy of having a smartboard. You can change these things as needed. Alright, that way it actually is drawn to scale. Once again, I'm moving this because I want to make sure that where I end is not as far back as where I began, because that's in reality. Okay. Motion maps don't have to be perfect, but we want to make sure they're drawn to scale as best as possible. So this would be an accurate motion map for the position versus time graph that's shown over here. Alright, let's look at another example. In this case, we're given the motion map. We now want to sketch the position versus time graph based off of this information. So, the position is in meters, the time is in seconds, and let's look what's going on here. So, it looks like we're starting right here because that's where my t equals 0 is. The original dot is not at the origin, so we know we're starting away from the origin, maybe somewhere up here. Then we see that the object actually starts at rest because there's no arrow coming out of this dot. So I'm going to actually draw a flat line right here indicating that I'm not moving. Then it looks like for the next 2 seconds the object has some velocity. Now the velocity here is going to be less than what it is later on, so I'll want to keep that in mind. Maybe I'll make my velocity kind of shallow. So for the next 2 seconds, let's say my velocity is about right there. Okay, so 1 and 2 seconds, the object is moving, and it's moving in the positive direction. Notice the arrows are facing the same way as the positive direction here, so I know it's a positive slope. The object remains stationary for 1 second, so I'm going to draw a flat line, and then for the next 3 seconds, 1, 2, 3, the object is moving back towards the origin, meaning the slope is negative. And not only is it negative, but it's going to be steeper because the double slash lines indicate that the magnitude is greater. So maybe what I'll do is I will do it like this. And actually I need to make it go to the origin because notice that's where it ends. So this would be a fairly accurate position versus time graph based off of the motion map. Once again, I knew the object was starting away from the origin, right here. It was at rest to begin with for 1 second. Remember, every dot represents one interval of time. So 1 second would indicate one dot, and it's motionless. Then for the next 2 seconds, the object 1, 2 is moving at a constant velocity. The object stops for 1 second right here. And then the object reverses direction, heads back towards the origin, and ends at the origin because the arrow lines up with the origin marker right here. And that's why I knew to make the line go all the way down here to the origin. Alright, looks like we've got 2 more slides. This slide right here. Given the following graph, determine how far the object went from the starting point. This actually is a little review, not having to do with motion maps, but simply doing graphical analysis. It wants to know how far from the starting point that this object went. So we're looking at displacement. Remember, we're looking at a velocity versus time graph, and that means by finding displacement, we're going to find the area under the curve. It looks like the shapes we're dealing with is a trapezoid and then a triangle. Now, I don't know about you, but remembering the area of a trapezoid is kind of difficult. So if you don't know the area of a trapezoid, what we can do is we can split this up into some smaller shapes that are a little bit easier to handle. So I'm going to split that up by making this into a triangle, a rectangle, and a triangle, and then a triangle right here. Remember, rectangles are base times height, and then triangles are 1/2 base times height. Okay, so for this triangle right here, the base is 10 minutes, the height is 60 minutes, so that's 600, but we have to divide it by half, or divide it in half, so that's going to be 300. For this rectangle right here, the base looks like 5, and the height is 60, so that's going to be 300. This triangle right here is going to go 5, 10, 15 is the base, and the height is 60. So 15 times 60 ends up giving you 900, but we have to divide by 2 because it's a triangle. So 450 would be the displacement for that. So altogether, if I added all that up, 1,050 meters would be the displacement for the first 30 minutes. Now let's look at the area of this triangle. The base of this triangle is 5, 10, 15, 20, 25 minutes times the height, which is negative 40. 25 times negative 40 is going to give you negative 1,000, but divided by half in half is going to give us negative 500. So the displacement here means that the object reversed and went back negative 500 meters. So altogether, if I added those together, the total displacement from the original starting point would be 550 meters. All right. The last practice I'd like you to do is this. If you read this problem, you'll notice that there's a little bit of a difference than what we've normally seen, and that is there's actually no question. Let's read it. An object starts at 10 meters away from the origin and travels away for 3 seconds at 10 meters per second. It stops for 2 seconds, then returns to the origin in 2 seconds. Sounds like a lot of information, and there's no question. The question is, what can you figure out? So what I'd like you to do is I'd like you to pause the video, and I want you to figure out everything possible that you can about this situation. I'd like you to sketch graphs, figure out information, motion maps, whatever you can. Pause the video and then hit play to reveal all the information that could be figured out. Okay, go ahead and take a look at what information could have been figured out. First of all, I went ahead and sketched the position versus time graph. Notice that we start at 10 meters, we go up in 3 seconds to the 40 meter mark, we pause or stand still for 2 seconds, and then we return to the origin in 2 seconds for a total of 7 seconds of travel. I transfer that over here to the velocity versus time graph, and I noticed just now that I did not label this. Always label your axes. So I have the time, I just forgot the velocity. Over here, I've mapped the velocity. 10 meters per second for the first 3 seconds, 0 meters per second for 2 seconds, and then negative 20 meters per second for the last 2 seconds. And that was figured out by taking the change in x over the change in t for this last 2 seconds here. I also found the area underneath the curves and used that to figure out my displacement. The displacement was negative 10 meters, indicating why the object would have started here at 10 and then ended at 0. I also took 30 plus negative 40 to get negative 10 as well. The distance, on the other hand, or ground covered, is 70 meters, because the object started at 10 and went up to 40, which is 30, stayed still, and then went back to the origin for 40 for a total of 70. The average speed, remember, is distance over time, so 70 meters in 7 seconds is 10 meters per second. Average velocity, on the other hand, is displacement over time. So negative 10 meters divided by 7 seconds is negative 10 sevenths meters per second. I kept it in fraction. You can also put it also in decimal as well. Either way is fine. So approximately 1.43 would have been the decimal version of that. It's amazing how so much information could be drawn out from such a simple problem. This concludes video lesson 3 as well as the video notes for unit 2. Make sure that you go through worksheets checking your answers to make sure that you are thoroughly prepared for the unit 2 exam.